Good evening, everyone. So today we will be discussing about biohydrogen, biomethane, and biomethanol production, as well as different methods in details. Mostly, we will be focusing on the hydrogen production via various biochemical processes and methane production. Just like biogas production as a part of methane production and methanol from the biogas. Okay, so in the introduction, I would like to give a brief details about some of the important points about the hydrogen uses or importance of hydrogen as a energy fuel. So we know that hydrogen is a colorless gas and it is having very high heating value. So it has 1 gram of hydrogen which can produce 142 kilojoule of heat, which is about 3 times of the general gasoline that we use. So if we can use the hydrogen in replacement of the gasoline, then we will get energy density high energy density fuel, and the cost will be minimized in terms of the overall operation, right? Now the product of the complete combustion of the hydrogen, if we use as a fuel, then it will be only water. So there will be a less pollution that will be as a less pollution occurrence as a result of the combustion of hydrogen. So it is a clean fuel you can consider. So hydrogen, which is kind to be our alternative fuel, is characterized as non-pollution or non-pollutant, high energy efficiency, and high recycling characteristics. Hydrogen is considered to be the most ideal energy dense fuel in 21st of century, but due to its extremely lightweight, because it is only H2, right? So it is extremely lightweight and it is inconvenient to carry and transport. So there are a lot of researches is going on to efficiently build up the hydrogen transportation or hydrogen carrier to transfer the hydrogen from one place to the another place. So we face lot of difficulty in hydrogen transportation because of the low lightweight and it the because of smaller molecular size, smaller gas molecules, so it easily can escape from the carrier or whatever. If it is suppose if you are transporting hydrogen gas via some tank or ship, that those are the convenient process of transporting the fuels. So at that point, if there is any kind of leakage, or there will be lot of hydrogen loss over the process, because hydrogens are very lightweight and very smaller gas molecules. So there is a lot of researches is going on. You can also refer to those latest research to follow up how the hydrogen transportation and or hydrogen storage is a big concern about the recent researcher studies. So hydrogen can be produced from various feedstock, including we know the conventional process of natural gas, coal, water, and now we are talking about the biogas. So hydrogen can be an input in the processes to produce various chemicals as well, such like we can produce methanol from hydrogen. We can also produce ammonia, hydrogen peroxide, hydrogen chloride, aniline, oxo, alcohols, and other chemicals. So hydrogen is not only a energy dense fuel and very important fuel. Other than that, it can also be the source for production of other various important chemicals, right? So there are a lot of hydrogen in methanol. So methanol can be also cracked in rivers to produce the CO, carbon monoxide and hydrogen through high temperature catalytic reaction. And then with it can be this hydrogen can be mixed with the methanol to form alcohol hydrogen mixture fuel for injection into the engines. So it can solve the storage problem of the hydrogen. Therefore, methanol can be used as the medium for hydrogen storage. So we can here we want to convey the message that we there is an option that if we have the hydrogen as a source, we can form the methanol, and we can transport the methanol as a energy carrier to the one place to the another place, and wherever it is required, then we can crack that methanol via high temperature catalytic reaction, and we can produce carbon monoxide and hydrogen, and then we can utilize the hydrogen. So now by that process, hydrogen storage can be done in terms of methanol production. So when we talk about the methanol itself, so it is also considered to be very promising fuel in the internal combustion engine with superior physiochemical properties than which is better than the other fossil fuels. So in the effort of replacing fossil based natural gas, so we know the natural gas is mostly containing methane, right? So we are in the process of replacing the natural gas via biogas, which is also an alternative of it is having also the main uh, gas composition as methane. So the International Energy Agency, they have reported that the global biomethane and biogas production could satisfy nearly 20% of the global gas demand if it is sustainably potential to be utilized in a full fledged. So modern facilities that produce the biomethane include also carbon capture. So we can also link the carbon CCUS project with the biomethane production, because carbon dioxide the carbon dioxide we are getting from a carbon capture process, that carbon dioxide can be used as a source for further utilization, right? Power to methane applications, wherever hydrogen is used, they can react with the carbon monoxide in the biogas, and they can upgrade to biomethane, which is also termed as synthetic methane. So typically there is 60% increase in the energy output in the form of the renewable biomethane formation. So now we already know there are various other methods for producing of hydrogen. So there are solar gasification method, thermochemical gasification method, some thermochemical process like pyrolysis, supercritical conversion. So these are some high thermal conversion processes. But we are mostly focusing in this lecture these biological processes, where we will be discussing of direct biophotolysis, photo fermentation, dark fermentation, and indirect biophotolysis, right? So here we can see that in combination with the steam reforming process, the production of the pure hydrogen is also achieved with a water gas shift reaction, which comes under thermochemical process. And the other thermochemical process contains like catalytic oxidation, autothermal reforming. Simple this pyrolysis is reported already here. Steam gasification. So these are the other methods of other thermochemical methods. So we will be focusing based upon these um, four processes in the further slide. So we just wanted to emphasize the fact that the worldwide production of the hydrogen currently exceeds 1 billion meter cube per day, which is around 48% is produced from natural gas, 30% from oil, that crude oil, and 18% from coal. And the remaining 4% only, which is being produced by water splitting electrolysis process. So mostly we are also as at this point we are mostly relying on the natural gas for producing lot of hydrogen. Those are around 1 billion meter cube per day. That is huge hydrogen production is still happening from natural gas, crude source, right? So now we will be discussing most of focusing on the biohydrogen production methodologies. There are different methods we need to understand it in details. So uh, yeah, so now the production of the hydrogen, which is being done from the biomass through various biological pathways, is also emerging technology considered to be it is very sustainable and eco-friendly. So there are different organisms, they can yield hydrogen under specific conditions, including microalgae that may use the light energy, solar energy or light energy to split water molecules to produce hydrogen. And that cyanobacteria, which is also one kind of green algae, they typically consume the carbohydrate to store energy from the photosynthesis, and then they produce hydrogen from the water molecule. So we will be discussing in details to clarify this particular point. So although there are striking advantages, but there are like low production rate, low substrate conversion efficiency, and the production and the accumulation of acid-rich intermediates metabolites from the acidogenic processes are practically they stands to be hindrance that should be overcome for the successful biological production of hydrogen in a larger scale. So in nature there are variety of organisms including archaea and anaerobic and facultative aerobic bacteria, cyanobacteria, and some low eukaryotes. So those are considered to be green algae and protists. They produce hydrogen, so which may function singly or it may be in a mixed culture, so they can perform to produce hydrogen. Okay, so the major hydrogen producing biocatalysts are typically heterotrophs in the fermentation process. So these biocatalysts are mainly bioenzymes. So some dark fermentative bacteria, they do not require solar energy because they are happening in a dark phase, so they do not require any solar energy as a energy source, and they can also tolerate anaerobic conditions or oxygen deficient condition. So these microorganisms are obligate anaerobes, which are further classified based on their sensitivity to the oxygen presence and their growth temperature. Briefly, uh, briefly, based on the systems that may evolve or produce hydrogen, there are a large number of different natural biological processes that can be categorized into basically four primary groups. First is water splitting photosynthesis. Second one is photofermentation. Third one is dark fermentation, and the last one is microbial electrolysis processing, which is very similar activity of the microbial fuel cell. So the selection of an appropriate biocatalyst or inoculum, it is obviously an important choice because we are dealing with microorganisms that will help to produce either anaerobic or aerobic conditions to produce hydrogen as a product. So we need to maintain or need to choose proper biocatalysts for the selective reaction to be occur. So naturally hydrogen is produced either by a single microbial species or by a mixed consortium of species, of which some of are involved in the production of the hydrogen, and rest they consume the hydrogen for their energy requirement or growth. So here we can see that these are some, you can see the microorganisms, those are involved in the hydrogen producing stage. There are typically two types: prokaryotes and eukaryotes. So depending on that, there is cyanobacteria and bacteria, and another one is the algae. So this bacteria, this comes under either dark phase or either photofermentation phase. So in the dark phase condition, there is fermented end product like lactic acid, butyric acid, butanol acetate, and mixed acid. On temperature tolerance, there are some bacteria are classified as thermophiles, mesophiles, and psychrophiles. So based upon the oxygen tolerance, depending on the bacteria classification, there are obligate, facultative, and aerobes. So these facultative bacteria, that is, they can grow with or without oxygen, preferably anaerobic, preferably in the presence of oxygen or aerobic condition. They can generate more energy through aerobic respiration. So when, if it is a condition like oxygen is absent, so they can switch to anaerobic respiration or fermentation. So those are called obligate anaerobes, and sorry, those are called facultative anaerobes. And for obligate anaerobes, they cannot survive in the presence of oxygen. So we need to ensure that these anaerobic bacteria should be in the complete isolated zone of the presence of oxygen. So lack of the enzymes needed to detoxify the reactive oxygen species in the obligate anaerobes condition. The another one is the algae. So for the photofermentation, there is two types of algae that we consider as a uh, initiator for the reactions, and those are very important for this reaction of hydrogen production. One is the sulfur, purple sulfur algae or non-sulfur purple algae, and another one is the green algae. So cyanobacteria, this comes under green algae. So when we talk about the production processes, these are some methods we are talking about for hydrogen production. So these are main two methods like fermentation and biophotolysis. In the fermentation, there will be two phase: dark fermentation and photofermentation. Where in the biophotolysis, there will be indirect biophotolysis and direct photolysis. So here, mostly what is happening, we will be discussing in detail in the further slide. So there are acidogenic fermentation is also lot of hydrogen is producing, whereas microalgae cultivation mostly biodiesel are producing, and in the methanogenesis bacteria production, we are mostly producing methane. And there are some other conversion processes like microbial fuel cell and also microbial electrolysis cell. Those are also helping to produce hydrogen from the biomass sources, and these two methods are very identical to each other. There is little bit of difference, but the mostly we are producing bioelectricity, where in the microbial electrolysis cell we can also produce the bioethanol as a product. So coming to the more detailed classification of the biohydrogen production methods, so there are basically three category you can see. One is the light dependent process. Second one is the dark fermentation process, which is light independent process, catalytic process, and third one is the bioelectrochemical system, which comes under microbial electrolysis cell. So, when we talk about the light dependent process, so it comes like biophotolysis or photosynthetic processes. So, here it comes direct biophotolysis process and indirect biophotolysis process. So, here what happens, algae with the hydrogenase, they participate. Uh, In the indirect biophotolysis, cyanobacteria with nitrogenous and hydrogenous, they participate for splitting the water into hydrogen ions. In terms of the photofermentation process, which is generally a single stage process, here what happens, they participate purple sulfur bacteria, or also there can be purple non-sulfur bacteria. So in the anaerobic condition process, they require this nitrogenous and hydrogenous enzymes as a biocatalyst, and they then then they produce the hydrogen by the reactions. And when we talk about the dark fermentation process, so here fermentation is like acidogenesis, anaerobic conditions, where carbohydrate is transformed into organic acids. So here organic acids like acetic acid or butyric acid formation, so there are separate pathway for the formation of different organic acids. So there is one advanced process, that is two-step photofermentation process, which is nothing but the combination of this step and this step. So in the two-step photofermentation process, which shows the higher yield of the hydrogen as a result by the research. So here what happens, in the step 1, we follow the dark fermentation process, where the hydrocarbons are firstly converted into organic acid and hydrogen, and rest of the organic acid is further converted into hydrogen by the second step, that is the photofermentation. So dark fermentation is followed by photofermentation, so the hydrogen yield is very higher for this case. And the last one we talked about microbial electrolysis cell, where mostly the acid like acetic acid, butyric acid, so these acid contents are converted into CO2 and hydrogen, not H plus ion. There will be molecular hydrogen we will get. So when we were talking about different enzymes, those enzymes are mainly acting as a biocatalyst for the hydrogen production process. So first is like biohydrogen production is mainly associated with two major categories of the enzyme. One is hydrogenous and another one is the nitrogenous. There are two basic category of the enzyme. So the nitrogenous is mainly associated with photofermentation process, where the purple non-sulfur bacteria are involved, and the hydrogenous, they mainly play in a single role for the algal bioproduction biohydrogen production process. So this hydrogenase, these are the enzyme which is capable of producing or uptaking the molecular hydrogen. Three categories of the hydrogenase have been reported in various microorganisms involved in the biohydrogen evolution. One is Fe hydrogenase, another one is nickel iron hydrogenase, and last one is the only iron hydrogenase. There are three category of the hydrogenase. These are some enzymes which will be having in their sources in various microorganisms. So mostly we will be talking about this Fe hydrogenase of algae, which has the capability to utilize very variety of the electron carriers like uh, peroxidins, then flavodoxin, sorry, and pyridine cofactors in different types of the organisms. And the nickel iron hydrogenase, they also be found out in different microorganisms, but cyanobacteria, they have extensively used in the biohydrogen production. In the next category of nitrogenous in enzyme, for this case, the primary function of the nitrogenous enzyme is to carry out biological nitrogen fixation. However, this process is always accompanied with evolution of the hydrogen gas in the second step. The nitrogenous is mainly categorized into molybdenum nitrogenous, which is very common type, vanadium, and iron nitrogenous. These are three types. So we didn't talk, discussed a lot of details about the enzymes because those are mostly a biological part. In details, you can also refer to any uh, existing uh, document, research document, to find out that what are the structure or what are the actual reaction mechanism, that how they follow the enzymes, they act for the hydrogen production. So in this class we have only pointed out that what are the different biocatalysts or enzymes are being used in the process of the hydrogen production. So now we will be discussing on the different methods for the hydrogen production. First one is the water splitting photosynthesis process, which is also known as biophotolysis. So this biophotolysis, this term refers that is splitting of the water molecule in the presence of the light by the photosynthetic organisms. Now this oxygenic photosynthetic microorganisms such as green algae. So there are some examples, and cyanobacteria, which is termed as blue-green algae. So the use in this process that require only water and sunlight as a main source, and by the utilizing of sunlight and water they will split the water molecule into hydrogen and oxygen biologically in the presence of the light energy. So this hydrogenous enzyme that we talked about in the last slide, this FeFe hydrogenous enzyme, which is a very complex metalloenzyme in the green algae, they drives the evolution of the hydrogen, whereas nitrogenous is responsible for the process in the heterocysteous cyanobacteria. The biophotolysis, the process is further divided into mainly two processes. One is the direct and another one is the indirect process. So in the direct photolysis process, what happens? The solar energy is directly converted into hydrogen. The electrons that we derive from the light energy, they mediate the water splitting, and then from the light energy mediated water splitting are transformed through photosystem 2, that is PS2 and PS1, to ferredoxin, and as a ferredoxin which acts as a electron carrier, and subsequently the ferredoxin they reduces the hydrogenous enzyme which is responsible for the hydrogen production. So what happens, that H plus ion, here Fe is reduced to Fd and hydrogen molecule is being produced. So let me. So what is happening in case of the direct biophotolysis? Simply I am writing that here water is splitting into hydrogen and oxygen through photosynthesis, you can say, because we are having light energy from the solar. So involved bacteria is cyanobacteria, and some green algae we are also using. So here we talked about the photosystem too. So here what happens that they absorbs light energy and they excite the electron. An overall reaction in the PS2, that is water, it splits into H plus ion, some electron and oxygen. So this electron pass down to the electron transport chain, and this proton, they are being used in the ATP synthesis, and the oxygen is being used like released as a byproduct. In the next step where PS1 is followed, there they absorbs another photon of the light energy and re-excites the electrons, and then they transfer the high energy electron to ferredoxin, that is FD. So uh, that's what we are talking. This FD is formed as a oxidized form, and hydrogen is formed as a molecular form, right? So ferredoxin is nothing but the acceptor of the electrons from PS1, and then they transfer the electrons to the hydrogenase, and then the hydrogen is being produced. Basically this hydrogenase enzyme, they receive the electron from the reduced ferroxidine, and then they these electrons then reduce the proton, that is H plus ion, into hydrogen gas. That is what it is happening in the direct photolysis. So however, the oxygen sensitivity of the hydrogenase, they hinder the efficiency of the hydrogen production. So oxygen concentration, if it is very high, then 0.1 percentage, they act as a transcriptional repressor and irreversible inhibitor for this hydrogenase catalytic activity, which is overall hindering the hydrogen production. Now we are talking about the next category, that is indirect biophotolysis. So in this process, the issue is tackled by temporal or spatial segregation of the oxygen and hydrogen in different evolution stages, coupled through carbon dioxide fixation process. So in the case of the indirect biophotolysis, hydrogen gas is produced by the photosynthetic cyanobacteria by a two-step. First step is oxygenic photosynthesis, which is happening in the vegetative cells, which generates different compounds like carbohydrate, and they release oxygen in the first step. So now followed by the second step, where the hydrogen production occurs in the heterocyst, where nitrogen fixation takes place simultaneously. Okay, so here that is what is happening, that hydrogen producing are being intensively investigated by this indirect biophotolysis process using the different cyanobacteria in the process. Yeah. So, in this method, the photolytic splitting of the water leads to the evolution of the oxygen in the initial stage, and the electron and H plus ion that are generated are used for the ATP generation and reducing power generation via photophosphorylation method, which in turn utilized for the CO2 fixation. Subsequently, the intracellular stored carbon is subjected to fermented, leading to the generation of the reducing environment, which is in turn used for the hydrogen production by the hydrogenase enzyme and nitrogenase enzyme in the later stage. So overall reaction for the indirect uh, biophotolysis, that is nitrogen, which takes the electron and proton as well, and 16 ATPA, that forms the nitrogen fixation in the formation of ammonia. It also produces the hydrogen in the process. So hydrogen production by the hydrogenase enzyme and oxygenic photosynthesis cannot occur simultaneously in the green algae. Thus, to obtain a sustainable hydrogen production, elemental sulfur deficiency, which causes a severe reduction in the photosynthesis, occurred within the cell to grow the acetate, resulting in the drastic decrease in the oxygen production rate coupled with the improved respiration. So, overall hydrogen production is increased. In this condition, the cells grown in anaerobic condition to produce hydrogen by using some of the electrons from the residual water splitting mechanism in case of the direct photolysis, and reversed carbon um, in case of the indirect photosynthesis. So this biophotolysis has a low solar to hydrogen ratio, and with the maximum reported we have seen 12 to 13%, while minimum is 0.87. So this conversion efficiency is not so high, but still it is being a very useful way to utilize the solar energy for the hydrogen production. So now we will be discussing the next method for the hydrogen production, that is photo fermentation process, and this is anaerobic condition because we are maintaining the oxygen free environment for this hydrogen production process. So this photo fermentation also involves the conversion of the light energy to biomass within the production of the hydrogen and CO2, and often the relation is nearly stoichiometric. This process is carried out by the anaerobic photosynthetic bacteria such as purple non-sulfur bacteria and green sulfur bacteria under anaerobic or oxygen-free conditions. So this process employs both. One is light energy, just like biophotolysis. Another one is the organic matter, which is the source of the hydrogen, like dark fermentation process. So this is the combined process, like photo fermentation. We are also using light energy and also using source of hydrogen. So major category of the photofermentive microorganism commonly utilized for the photofermentive biohydrogen production include, we have talked, like purple non-sulfur bacteria. This purple non-sulfur photosynthetic bacteria show a very high level of the metabolic flexibility, and they do not possess the pH2 system, hence they can be carried out easily in the anaerobic photosynthesis conditions. One of the most significant enzyme which is involved in the biohydrogen production is the oxygen sensitive nitrogenase enzyme. So when we are maintaining the anaerobic condition, so it will allow its proper functioning of the nitrogenase enzyme in the oxygen free environment without it being adversely affected by the oxygen, because we are already maintaining anaerobic condition. So this nitrogenase enzyme will be acting efficiently. Now the purple non-sulfur photosynthetic bacteria, they include some of the examples have been given, like rhodobacter species. They are used to convert the organic acids, just like acetate, lactate or butyrate. These acids they are converting those acids to hydrogen and carbon monoxide in the anaerobic and ana- this anaerobic conditions. So these acids, this acetate, water and light energy in the mixture like in the overall reaction, it is ultimately giving carbon dioxide and hydrogen. Moreover, these PNS bacteria, they capture the solar energy to transform this organic acid into hydrogen using some nitrogenous enzyme in the absence of the ammonia ions. Now, in particular, when oxygen sensitive nitrogenase is not a problem for this process, because the purple bacteria used in this process already they have non-oxygenic photosynthesis method. However, this nitrogenase they also possess several defects that may affect the production of the hydrogen. Like it has some low catalytic activity. Also, there is suppression issues of their expression if there is presence of ammonia, and also there is comparatively lower photochemical efficiency. In theory, the photofermentation process can completely convert organic compound into hydrogen, even reaching a comparatively higher hydrogen partial pressure. Simultaneously, hydrogen production it is driven by the nitrogenase enzyme, and the ATP is formed with the capture of the solar energy through photosynthetic mechanism using this bacteria. So these are light dependent processes. Okay, this still now we are discussing the processes which are light dependent process, where the capture of the light energy drives the electron stream through the photosynthetic system and leading to a proton gradient, and that will further fulfill the requirement of the nitrogenous enzyme activity like ATP production or ATP synthesis, then high energy electron transfer and generated through electron flow. So overall there will be a higher activity of the nitrogenous enzyme in this process. So next process is in the absence of the light energy, which are talking about dark fermentation process. So this dark fermentation process, they also produce hydrogen using facultative bacteria or obligate anaerobic bacteria. Now the process of the dark fermentation occur very higher rate than other processes like photofermentation or biophotolysis. However, the lower yield of the hydrogen on substrate basis, because the formation of the various byproduct that happening in the intermediate of dark fermentation, like formation of the acetic acid, butyric acid, so this kind of even formation of alcohol, they may be creating hindrance in the overall yield of the hydrogen. So dark fermentation involves the use of the anaerobic microorganism in the absence of light energy. They maintain temperature 25 to 80 degrees Celsius at a even sometime at a higher temperature than more than 80 for the biohydrogen production. So in addition to hydrogen production, there are other gases like carbon dioxide, carbon monoxide, hydrogen sulfide. Those are also released in these conditions. So a primary source of the biohydrogen production is the glucose molecule that occur in the carbohydrates and other feedstock. So they utilize those glucose molecules and follow the different pathway like acetate pathway, butyrate pathway, or here propionic acid pathway to ultimately they produce the carbon dioxide following those pathway. The byproduct which is generated during the reactions, they are some volatile fatty acid. Significantly, they may affect the yield and productivity of the biohydrogen. So in particular, glucose can be converted to 4 moles of the hydrogen per mole of the glucose substrate. If you are using acetate as with acetic acid as a co-product and 2 moles per mole of the substrate of butyric acid as a co-product. So these are some intermediates, like these acids and intermediate. Thus acetate is the preferred metabolic pathway as it can produce more hydrogen than the butyrate. Besides, there are hydrogen gas formation depends also other process parameters like pH, retention time, hydraulic retention time or HRT, partial gases of the hydrogen produced or other gases produced. So operational parameters of the bioreactor can be changed to control the hydrogen production process. And also we are getting hydrogen and a lot of other gases. So biogas synthesis also an important product of the dark fermentation that contribute to overall biohydrogen production. Now biogas synthesis like biosyngas is a gas which is rich of carbon monoxide and hydrogen, typically concentration 36% carbon monoxide, 32% hydrogen, 30% of the carbon dioxide, and 11% of the methane, and some trace element. So this biosyn gas is also a product of the dark fermentation process. So owing to non-dependence of the light in this process for hydrogen production, dark fermentation presents several advantages, including the possibility of continuous hydrogen production, lower energy input, as well as it offers greater ease of us upscaling and controlling. Apart from this, dark fermentation can also make use of various waste material like food waste or wastewater as a substrate, and hence the potential of providing a bigger field for the energy generation by utilizing the waste disposal. Now, the researchers have suggested the utilization of combination process that we talked about in the 2 3 slides back, that involving of the dark fermentation and photo fermentation, combining these two processes that will be better for producing more hydrogen, biohydrogen, where the byproducts of the dark fermentation will be utilized in the photosynthetic microorganism in the next stage to more make the greater yield of the hydrogen. Also in the growing scale of the nanotechnology, so the nanoparticles such as Ag plus or Fe3 plus, TiO2 minus or nickel ions, so this can be a game changer in the area for because they can improve the efficiency of the dark fermentation or photo fermentation processes to overall improve the yield of the biohydrogen production. So when we are comparing the these processes, so we can see that dark fermentation process where light is not required, it saves energy, beneficial beneficial byproducts, or we are having acetic acid, lactic acid, those are produced and those can be used. They maintain the anaerobic process, so saves also the aeration cost. Photofermentation, they maintain the nitrogen, atmospheric nitrogen fixation because they produce NH3 as a product, and uses the light energy wide spectrum possible, and absence of light absence of light is not mandatory for this case because this is photofermentation, this is light dependent mechanism. And for the combined process of dark and photofermentation, so absolute conversion of the substrate to hydrogen, we are getting higher yield of the hydrogen, and effluent is safer with low COD value. So it is highly useful for the water treatment process. Whereas disadvantage like dark fermentation, the oxygen removal sometimes it is very critical because, and also it is if there is any oxygen presence that may inhibit the activity of the hydrogenase, and substrate to hydrogen conversion efficiency is somehow lower in case of the dark fermentation, and higher yield achievable under thermodynamically favorable conditions sometime. And we are also getting some product mixture of the gaseous mixture, and we need to remove the CO2 before we want to separate the hydrogen from the mixture, right? And photo fermentation process where oxygen removal is very critical sometimes, and there it also suffers low efficiency conversion. And this two stage combined process where the physiochemical conditions they require extremely critical control over this volatile fatty acid buildup, because this can be also a limiting factor. And the carbon nitrogen ratio for the nutrient medium, so these are also very important for to maintain in these two stage processes. When you talk about theoretical hydrogen yield, so in the dark fermentation we have 4 moles of hydrogen per mole of the substrate, and in the photo fermentation 8 mole of hydrogen per mole of substrate. And when we talk about this combined technology, then we are getting very like 3 times higher, like 12 moles of hydrogen per mole of the substrate. So we can see this combined stage or two stage by process is very effective for higher yield of the hydrogen production. So next part for the hydrogen production, that is the microbial electrolysis cell. So this MEC or microbial electrolysis cell are green technology that combines the operating principle of an anaerobic biomass reactor and an electrochemical cell where the water electrolysis is happening. So this MEC has similar construction like microbial fuel cell, which is having two electrode, anode and cathode, separated by an ion exchange membrane. So unlike microbial fuel cell, this new generation MEC requires some external energy support to carry out the cathode chambers reaction. The hydrogen production on the cathode of the MEC in this electrohydrogenesis process is not a spontaneous process. So we need to supply the external energy to make the reaction to occur, because we are producing a H plus. From the H plus end we are making it H2. So this is not a spontaneous reaction, so we are giving the external energy to make it happen. So theoretically the additional voltage required for getting hydrogen from MEC is nothing but energy of cathode minus energy of anode. The microbial electrolysis cell they exploits the conductor like properties of the electrogenic microorganism that catalyze the electrochemical oxidation process of the organic substrate. They convert the electrical energy to chemical energy stored into hydrogen molecule that is produced through the electrochemical reduction of the proton of the electrolytic medium. So the main advantage of this technology is the ability of treating wastewater effluent, which is nothing but the source of the organic matter content, and also synthesizes the biohydrogen simultaneously. The production of the hydrogen is very essentially it is dependent on the type and the concentration of the substrate which is used or fed into the MEC. The most common substrate used in the MEC is acetate, glycerol, glucose, cellulose, which are present in the wastewater. So in this process, the exoelectrogenic bacteria in the anode, they consume the organic waste in the absence of the oxygen, and they convert, and from the organic waste they discharge electrons to the anode. in the presence of the a small input power, and electrotrops in the cathode, they receive the electron and transfer this electron to the cathode via external circuit to generate methane. The hydrogen and methane generated from the MEC for can be used to as a fuel in the IC engine for productivity of the electricity. So this MEC has higher hydrogen recovery and wider substrate diversity compared to the dark photo fermentation or MFC. So the efficiency of the hydrogen production is highly affected by the type of the substrate that you are using as electron donor in the anode. So when we are talking about, suppose we are taking acetate as our substrate. So what will be the process happening? So in the anode, this acetate presence in the presence of water, it will be giving proton and electrons. This electron will pass through the external circuit to the cathode, and from there, and this proton will pass through the um, membrane, ion exchange membrane. They pass to the cathode, and from in the cathode section, this electron and proton, they form hydrogen. So when we are getting the overall reactions, it is nothing but this acetate in presence of the water molecule, they form carbonate ion H plus and molecular hydrogen. So the final reduction of the protons to the molecular hydrogen is thermodynamically non-spontaneous. So we need to give external energy to make the reaction happen in the cathode. So now we will be talking about the methane part, that is mostly coming from the biogas. So biogas production is based on the anaerobic condition, which can utilize a wide variety of the organic feedstock like municipal organic waste or industrial organic waste, agricultural residue and plant material, etc. we can use for production of the biogas. So we can also produce the biogas through thermochemical processes, but today we will be discussing the biological process, or so that's basically anaerobic digestion process for the production of the biogas. So anaerobic digestion, they takes place at a temperature of minus 60 to 10 degrees Celsius, which is very suitable also in the normal temperature range, room temperature like 30 degrees Celsius. Additionally, we need to maintain the pH in the range of 6.8 to 7.2, and the carbon nitrogen ratio nutrients also play a big role for the biogas yield. Now this biogas comprised of the 55 to 70% of the methane, mostly it has methane. Also, it has part of CO2 and very small percentage of the nitrogen, hydrogen sulfide, these gases. So biogas needs to be upgraded to get methane concentrated to term as biomethane. So this biomethane is a renewable gas with almost identical properties like natural gas that we use, and it can be fed to the existing gas infrastructure and can rely on the proven technology for its transportation and utilization. So within specific industries as well as municipality like gas boiler, combined heat power exchanger, so we can replace the natural gas with the biomethane very easily because it has very similar characteristics. So industry is a major source of the organic material, which is much of which is not being valorized it. So we can use those industrial waste as well to reduce the carbon footprint and improve the environmental impact. We use the technology of anaerobic digestion to make major source of the biogas. This biogas can be burnt with a blue flame and temperature around 800 degrees Celsius, and this gas is mixed with air in the ratio of 1 is to 20 and very high ignition speed. So 1 cubic meter of biogas, which is equivalent to 0.4 kg of the diesel fuel and zero point 0.6 kg of the crude oil, zero point 0.8 kg of coal. In general, to produce the biogas, organic materials should be mixed with same volume of the water, and after homogenization, it should be poured into the digestion chamber. After the appropriate retention time, pH and other thing, methane gas or biogas is obtained. And of course, the production of the methane gas also follow various optimization of the process to get more economical production of the biogas. Now, anaerobic digestion is completely a bacterial process. That's why it involves various bacteria. So, there are 5 different phases through which the biogas is being produced. In some cases, for the quick start of the digestion reservoir and faster decomposition of the material in the reactor, chemicals such as sodium carbonate, minerals such as sodium carbonate and minerals such as nickel and molybdenum, it's etc. are used into the reservoir to increase the alkalinity of the system to speed up the production of the biogas. So, talking about 5 phases for the biogas production. First phase is zero phase. In this phase, the fermentable organic material are prepared and separated from other impurities, and those are mixed with homogenized with water, and then it is transferred into digestive reactor where the reaction takes place. In the first phase, the anaerobic bacteria use enzymes to break down the larger molecule of the organic substance such as protein, carbohydrates, cellulose or fats into some compounds with smaller molecular structure. So these bacteria break down the complex structure into volatile fatty acid. In addition of the acetic acid, propionic acid, ammonia, carbon dioxide are also produced in this digestive process as a first phase, and the transformation of the heavy molecules into small molecules which are composed of the substance such as hydrogen, carbon dioxide, fatty acid, ammonia, amino acids, which is provided by a group of bacteria called aquatic bacteria. In the second phase, the acid forming bacteria lead to the breakdown process to the formation of the biological acids acids such as carbon dioxide, hydrogen sulfide and ammonia. So at this stage, the acid forming bacteria convert the organic compound into volatile acids. Proteins are first break down into amino acid and then it transformed into volatile acids. Carbohydrate are first converted into simple sugar, then it is transformed into volatile fatty acid. So all the fatty acids are being formed. Then in the third step, the acid forming bacteria which produce carbon dioxide, hydrogen acetate, hydrogen sulfide, ethanol and very small amount of the methane, nitrogen and ammonia gas. So in the third stage, methanogenic bacteria, they start decomposing the acids which is being produced in the second stage to produce methane and carbon dioxide as a final product. So this group is made up of a small number of the bacteria that grow and reproduce very slowly, and which is very sensitive to their environment or nutrient pH and other thing, C by N ratio. So in a properly functioning digestion reservoir, the balance of the two groups of the bacteria should be such that the mechanism start like only the acid produced by the acidifiers. Some of the other types of bacteria, they use hydrogen and carbon dioxide to produce methane. So mainly the methanogenic interactions are taking place in the third phase. In the fourth phase, where the methane production phase, methanogenic bacteria started producing methane, carbon dioxide, and alkaline water. So bacteria in the methane phase or the fourth phase need more time to reproduce than in the second acid phase. So and the growth is declining, because we are making it alkaline medium, like subsequently. So the growth is being, the reproduction stage also is being delayed. So the rate and the scale of fermentation depend on the bacterial metabolism for the methane formation. So now you can see the different stages of converting the organic matter into the biogas. So complicated bioorganic material are followed by hydrolysis and fermentation, where different organic acids are produced. They follow the acetogenic path to produce the hydrogen and carbon dioxide, and here the acids are formed, and from there, in presence of the methanogenic, they form um, CO2 and methane mixture. And another forms, they also form H2S and CO2. So this, before utilizing this biogas directly into the system, we need to eliminate this CO2 and H2O, which is being done biogas purification process. So biogas purification process, which will be discussed in the few slides, in later on in the few slides after. So now we will be discussing about the biogas reactor. First one example, there are a lot of variety of the biogas reactor, but I have represented some of the types that you can have idea about the biogas reactor type and the mechanism that are followed in the different types of the biogas reactor. So first one is the CSTL, which is very common reactor. Okay, so here the effluent is being fed by the pumping, and it is transformed into the CSTL reactor, where continuous stirring is being taking place, and this is the sampling port, and the whatever the biogas is being produced, that will be collected from the top of the reactor. So this steering, mechanical steering we are having here for inhibit the precipitation and better mass transfer between the organisms and the substrate. So when these reactors are fed with high amount of the organic matter, the acidification occurs very promptly and resulting in the production of the volatile fatty acid that will inhibit the volatile fatty acid, and higher amount of the volatile fatty acid that may be inhibit the anaerobic digestion process. So for this case, this reactor is usually used as the fermentative unit in the two-stage anaerobic digestion process, Now the concentration of the microorganism in the CSTR configuration is very relatively low. We keep it relatively low, and it is not suitable for higher organic load content to produce biogas. So definitely the incoming feed to the CSTR that should have lower, not so much high content of the organic matter. Otherwise there will be not sufficient interaction between the microorganisms and the substrate, so ultimately the biogas yield will be low. Second type that I have presented, that is the anaerobic membrane bioreactor, where the membrane uh, it is like the treatment is conducted using the membrane filter, which guarantee the proper biomass accumulation. So here the general structure of this reactor that is very similar of the CSTR, but here we are using the membrane filter as a packing material. So this external membrane filter configuration, which this membrane unit which is separate than the main reactor, the mixed liquor is fed under pressure from the bioreactor to the from the bioreactor to the membrane unit under pressure, and membranes working at a tangential flow and under pressure condition, the permeate will be discharged and the retardant will be recycled back to the reactor, and permeate will be discharged as a biogas outlet. So they are widely used for the wastewater treatment process, as they can control the solid concentration and the hydraulic retention time. So producing an effluent with the high quality terms in terms of the COD and total suspended solid, it also there is high maintenance um, of the slow growth microorganism as methanogenesis, which is used. So the main disadvantage of this reactor is membrane fouling. There is high chances of the membrane fouling, which decreases the membrane area available for the further fil- filtered filtration. Sorry, and overall the operation cost will be high. The next reactor type is the horizontal anaerobic immobilized bioreactor. This is kind of the fixed bed horizontal reactor. So it prevents the biomass to be washed out. Like how? Because here we are using some supporting material, and which is being nothing but polystyrene particle or polyurethane foam, or otherwise we can use also sand particle. So that will not allow the biomass to be simply wash out from the reactor. So overall, these materials results in the better growth of the microorganism. This high L by D ratio of the reactor contributes to better stability of the overall process. Okay, so the materials are fed by the pump at the one end and leaves the reactor th- through the other end, and when it comes to the microorganisms and passes through the supporting material, the biogas is produced and that may be collected from these outlets. So growing of the biomass concentration in the reactor, that will improve the rate of degradation, and also that may raise the resistance to the existence of the toxic material and the shock loads. So it can also handle the higher concentration of the biomass to make efficient biogas production. The next type, that is the half-flow anaerobic sludge blanket type bioreactor, which is an example of very high rate reactor to treat the industrial wastewater. So the formation of the highly these granules particles are there. So these settleable granules represents a highly alternative retained cells, which is self immobilized without requiring the support external support media. So this granule particle that will enhance the uh, this mass transfer efficiency, and this three phase separator at the top here located, that will separate the granule particles and the biogas. So the granule particles will further come down and the biogas will be collected from the top. So this reactor produces methane as a very maximum efficiency, um, and very low sludge production we can use. This is very useful. Okay, next type is the anaerobic fluidized bed reactor, which is having in non-fixing supporting material. So they use the biofilm covered carrier particles like sand or activated carbon or other synthetic media that will allow the microbial attachment. So this enhances the microbial concentration, leading to better degradation efficiency. So existing biomass in this reactor, which is not being simply washed out because of the immobilization on the supporting materials or particles. So there is some substrate they ascend by drag force and leave the reactor. The steering option is performed. There is no such external steering for this case. We are having these granule particles that will be in fluidized condition, and that will create the vigorous mixing. So due to high biomass density, the reactor can be smaller than the conventional AD digester, and here we there is a faster rate of the biogas production in this case because of the higher efficiency of the fluidized bed reactor. Next one is the fixed bed reactor, which can be two types like ascending or descending reactor. So in the descending type, the feeding is introduced from the top of the reactor and leaves uh, here it is a descending type though. So feeding is introduced from top of the reactor and leaves through the bottom of the reactor once it is passes through the supporting material. So these are the supporting material where on which there is biofilm on the material surface. So there will be degradation happening when it comes in contact with the microorganisms film or the biofilm over the supporting material. Typically polyethylene or gravel or activated carbon or polyvinyl chloride, these are some supporting material that are used and on which there is biofilm attached, so that there is higher rate of the biological degradation. The next type is the packed bed reactor, anaerobic packed bed reactor. So they are packed bed. The support is usually adapted to allow the biofilm development. So here the retention time of the microorganism is very high due to cohesion to the support and thereby extending the retention time of the solid in the reactor. So this reactor neither use any mechanical agitator, not any use of the recirculation like fluidized bed. But here the packing material, they have the addition of the organic organisms, and this microbial population, they help to degrade the bio material to produce the biogas. Here you can see these are the several sampling port to optimize the process, like to monitor overall the process. Now, last one, there is a exceptional example of hybrid anaerobic bacteria. Reactor. So this reactor has originally designed for the treatment of industrial wastewater, those having very high organic load they have. And here what happens, there is combination of the half flow anaerobic sludge blanket type reactor and also anaerobic filter. So what is happening in the bottom of the reactor of this hybrid reactor, that is the um, half flow anaerobic sludge blanket type, or the granular sludge is retained. Okay, so the influent weight comes and flows upward, interacting with the sludge blanket where the anaerobic digestion occur, where the organic matter are converted into biogas. So here it comes that follows the upper part where there is a fixed or suspended biofilm carrier media. So here require further breakdown happening on the residual organic matter, and there the overall treatment efficiency increases, so there will be higher yield of the biogas. So this again, this hybrid reactor efficiency is higher than the individual one. So other type of bioreactor are also present, biogas reactor. So you can follow this a particular um, research article to follow more information of the regarding this biogas reactor in details. So the next part is like we have discussed about the biogas production method, biogas reactor, those are involved into the process. Now we need to discuss about the biogas purification process. So I will be not discussing so much detailed about the purification process, because there are a lot of purification process that we generally have, but industrially we have some of the like absorption adsorption technologies, which are very mature technology for the biogas purification. So in the biogas we have seen that apart from the methane content, there are other gases as well. Those are also acidic gases like CO2, H2S, those are present. So this conventional biogas upgrading technology generally focus on the CO2 removal due to relatively higher concentration in the raw biogas. So however, the raw biogas also have H2S trace amount, that maybe if you are not eliminating or reducing the content of the H2S, uh, that may cause difficulty in the end use application, which is because H2 is also toxic and corrosive in nature. The NH3, siloxanes, or volatile organic compounds are other unwanted pollutants in the raw biogas, usually present in much lower concentration than H2S. Suppose, for example, if NH3 is present, that may induce corrosion in engines, pipelines during the combustion process. If the siloxane are present, so they can form the microcrystalline quartz and deposit on the engine surface, resulting in the abbreviation or overheating or malfunctioning of the engine or even valves. So, if you are supposing like volatile organic compounds are present in the biogas, so depending like upon combustion of the volatile organic compounds, they form benzene and other organic compounds which are very unpleasant smell, gives unpleasant smell to the biogas, and typically potentially like toxic to the human health. So conventional physiochemical methods for the biogas upgrading achieve methane recovery which is greater than 96%, but are highly energy intensive and large economical, like large environmental impacts. So among all the biogas purification techniques, water scrubbing or chemical scrubbing, pressure swing adsorption, membrane separation, even hydrate formation. So these are some purification technologies are existing in the market. However, these physiochemical methods have several limitations. Like some of them, they use, if you are doing the water scrubbing method, they use lot of water for that. Maybe also having the concern of water shortage and high electricity cost. Okay, so because the pressure swing process, applying high pressure condition, that is also a concern, and that consumes lot of energy overall the process. If you are doing the chemical scrubbing process, they use the amines and different other chemicals that also subjected to thermal and oxidative degradation. Also, this H2S removal is also very important when you are doing for the membrane separation process. So to promote the sustainable development and environment friendly technologies that we opt for, these biological methods also are available for biogas cleaning, like depending on the biogas, we can convert it into biomethane production and water gas valorization. So this kind of other biological environment friendly options that we should opt for uh, to basically towards a like sustainable process other than this physiochemical process, because they also use lot of energy and water consumption over the system. So we will discuss some examples of the biogas purification process. First one is the CO2 removal process. So here what is happening, this is the physical absorption is happening. So absorption column and desorption column is there. So here what is happening, that difference in the solubility of various gas compounds present in the biogas, uh, it is the main concept that we are having in the physical absorption process. So here in the biogas scrubbing method, where the packed bed is used in the absorption column, different kinds of packings are also introduced in the co-current method of higher gas to liquid mass transfer. So here what we can see that this water also, that water scrubbing also can be used in this process. And when we use the organic solvent method for this process, like methanol or dimethyl ether of polyethylene glycol, this also can be employed for the CO2 removal. So this is the overall physical absorption process. So coming to the chemical absorption process, it incorporates the use of different chemicals such as monoethyl amine or diethyl amine, or alkali solution like KOH solution or K2CO3 solution. Sometimes sodium salt solutions are also used for as a chemical absorbent. Okay, so here what we have, that there are certain difficulty in the process, because also it needs very high energy for the desorption process to regenerate the solvent in this process. Also there is but sometimes what happens, that amine solution is widely chosen for this process because those are highly selective to the carbon dioxide removal. So this chemical absorption technology is very mature in the industrial scale. The third one is the pressure swing adsorption process, where where adsorption, depressurization, then desorption, and then again pressurization. This cyclic method is being followed to separate the CO2 from the biogas system. So this is like most commonly used absorbent is geolite we can use. Then activated carbon, it is used as a adsorbent, and other things like silica gel, those are used in the adsorbent process. So they can be used to separate the carbon dioxide, nitrogen, oxygen, even hydrogen sulfide from the gas mixture by selective adsorption. Okay, selective adsorption of CO2 is happening over methane onto the porous adsorbent and with a very high specific surface area. Since methane molecules are very larger than the other gas molecules, so only the CO2 will be adsorbed onto the adsorbent, and then it is followed by depressurized. Um, to release the CO2 nitrogen mixture, and after that we are getting upgraded methane from each of the point, because we are removing the waste of gas, like water gas and carbon dioxide from the each point, because selective adsorption is happening over the process. And this pressure swing means this high pressure adsorption is happening, then depressurization is happening. So these are the process, cyclic process is being followed for separation of the methane and carbon dioxide. Then it comes cryogenic separation method. Cryogenic separation method, that CO2 has a CO2 has freezing point like -78, and methane has -160 degrees Celsius. So it results like CO2 separation can also be done by cooling the gas mixture at a elevated high pressure and low temperature condition. So the problem, only problem is the energy consumption is very high when the biogas is compressed at a 200 bar or around that. So this is very energy intensive process. The third one is the membrane separation. This is also being widely used for the process, but here mostly is the selective permeability is being concerned. So selective permeability of the membrane, which is mainly responsible for this gas separation process or gas liquid separation process. So the liquid solution can be amine, or the system which is highly selective compared to the solid membrane system. So here what happened, the gas separation works at a higher pressure, around 20 to 40 bar pressure is maintained, or it can also work as a 10 to 18 bar low pressure conditions. So resulting we will get like 80% around methane from this methane separator. And then at the last, like high purity of the methane can be achieved in the several membrane series that if you are using, not single membrane. If you are using multiple membrane, then we will be getting more than 80% of the methane as a output. The last one is another method for like biological methane enrichment, where the microbial conversion of the CO2 and hydrogen to methane formation is based on the ability of the hydrogenotropic methanogenic bacteria, which has the capacity to utilize the carbon dioxide as their carbon source, and the electron acceptor, and hydrogen as a electron donor, and they form the methane out of that, utilizing carbon dioxide and hydrogen. So this is also a new that I was talking about, this biological and sustainable process for utilizing the other gases like carbon dioxide, hydrogen, and that can be converted into more enriched methane biogas. So there are some examples of the microorganism that can be used for this conversion. So when we are comparing the carbon dioxide removal technologies, so we can you can refer this slide later on to have more detailed knowledge about the advantage and disadvantage. So I am skipping this slide as of now. You can refer this slide later on. Coming to the hydrogen sulfide removal, so there are certain in for hydrogen sulfide removal technologies, that also have physical and chemical absorption process, where we use different methods like select sol method, also chemical absorption by utilizing the chelated. Selection is physical absorption method. Chelated Fe3 plus EDTA solution. This is for chemical absorption. These are some example for removal the H2S from the mixture. Another method that it follows like adsorption of adsorption using activated carbon sources. Uh, Also, there are biological methods as well. Biological desulfurization and biofiltration process or H2S. So I'm not giving in detail because these are some thing you can refer in detail. I will share the supporting documents to refer these processes in detail. I will share in the Google Drive. So you can here also see the advantage and disadvantage happening with different type of H2S removal technologies. You can refer this, and also you can refer the supporting document that I will be uploading in the Google Drive. Last portion, that is the methanol production. Methanol also, obviously it is a building block for many production of the other chemical. Also, it is considered to be a clean burning fuel with high energy density and long term potential for the shipping sector. Traditional processes for methanol synthesis mostly rely on the gasification process or natural gas reforming process, but the biogas to methanol production process is something that is taking interest of, and that can replace the natural gas as a feedstock for the reforming section. Now, the biogas to methanol conversion processes basically consist of three sectors, that is biogas pretreatment, then biogas reforming, and then methanol synthesis and purification. So this methanol synthesis is favored by high pressure condition 50 to 100 bar and temperature around high temperature 200 to 300 degrees Celsius. The catalyst use copper or zinc oxide catalyst, often stabilized, that is alumina supported copper or zinc oxide catalyst are used for this process. So you can see in the process that biogas, first it is sent for the CO2 removal, and then it is CO2 removal or other pretreatment has been happening, and then it is sent to the biogas reforming section, where it is like from the biogas it is forming the methanol. Okay, so the syngas along with the methanol, then again the CO2 is being removed, the compressed and the methanol synthesis is being done in the, sorry, it is, this is a steam reforming process. Steam reforming process, that is like all of the carbon monoxide and carbon dioxide it forms in the mixture of carbon dioxide and methane, and the all of the CO2 removal is happening after that, and then it is compressed and sent for the methanol synthesis, and from the methanol synthesis is followed by the methanol purification process. So this is very simple process. It only follows the um, it only follows something like proper pretreatment process of the biogas, and it follows the methanol purification. So this methanol can be a building block for other chemical synthesis, and also it can be used in the IC engine as a fuel, and this methanol, after breaking down the methanol to hydrogen, it can also have the like vice versa, we can also produce the hydrogen out of that, and also act have the potential to act like a hydrogen carrier. So so that's all for the today's class. Is there any question that you want to discuss? In the next class, we'll be discussing some of the acid production during these biological processes that we can consider and discuss in detail in the next class. I'll be sharing all the supporting document for this bioreactor part and other thing. This hydrogen and CO2 removal, that biogas purification part, that two supporting document I'll be attaching in the Google Drive for your better understanding in detail, because that much detail is not possible to cover in this lecture. So you can refer those detailed in the supporting document. Okay, if there is no further, is there any question?
Yeah, could you please share that your slide? I think it is 25, slide number 25 regarding cryogenic purification.
Okay, so you want in detail about that.
Yeah, in that slide you have mentioned that that biogas which is produced is going through so many compressors, and once the gas is going through the compressors means obviously the pressure and temperature also will increase.
The
And where is that cryogenic part is coming? Cryogenic part means it is temperature at
low
lower.
temperature, yeah. So depending on the like freezing point of difference in the freezing point of carbon dioxide and methane, we can utilize that property and we can separate the CO2 and methane. So okay, I will share the cryogenic, uh, you can say cryogenic distillation as well. Okay, I will share that part as well in the Google Drive in detail.
Okay.
Okay, then thank you for
One more,
joining.
one
Yeah,
more thing. Actually, it is a suggestion from my side. If
yeah.
you don't mind, could you please have some question? That means a discussion of questions in the last part of the class as well, because by the name itself, it is a problem-solving session, and we are not seeing any kind of problems so far here.
What kind of problem solving you want to solve? The what the assignment questions?
No, I'm not asking to solve the assignment questions. At least some kind of assignment questions you can bring it and solve it in the class, and
See,
so that we can easily solve the assignment questions. And so far, I did not find any kind of numerical problems. I don't know whether the numerical problems will ask in the examinations. It is purely we are
in
going
the
through this.
in the assignment questions, is there any numerical questions as of now that you are?
No, assignment questions also I didn't find any numericals, but I don't know whether in the examination what will be the condition. But some other Swayam.
Sources.
Yeah, yeah, it is. I am
Yeah,
facing that as a problem. I don't know what
yeah.
will happen at the end of this 12 weeks at the time of examination, whether they will ask numericals or not.
Okay. So I think this lecture is more about like I also been part of inorganic chemical technology before, so there also that was completely theoretical part of the subject, and this lecture also having theoretical part. So I don't think there will be numerical questions. If you are if you are joining some other courses like fluid mechanics or other like environmental engineering something, so they have lot of numerical questions to discuss. So I will try if there is any because
Okay, I will give you one example.
yeah.
Okay, and, if you don't mind, you please go through the that bio waste biomass conversion. That means bio waste to energy. Waste to energy conversion. One 8 weeks course is there. Actually, one Mandal sir is conducting that course. Uh, Actually, it is similar to our this present course, but it is having so many numericals. And recently only I have attended that examination, but I find it was very difficult. Very difficult means that examination. It was so they asked so many numerical questions.
So they also have those discussion of some numerical questions in the lectures as well, right? If
Yeah,
they
it is there. It is there. It is there. It is
Yeah,
there.
so if
Uh,
if the numerical part comes into picture, then it will must be discussed by the like professor, like who is taking this NPTEL lecture as a main guide. So he must have include the this
Tutorial part.
tutorial part as well. So if you are attending the online classes for NPTEL.
Yeah, it is already over. It is already over. I have already attended the examinations.
No, this for this course.
Yeah, attending.
Okay, you can ask there, right? So if there is because for my I will be not setting the question. So if
No, 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 no. I am not asking the questions and all these things, but that probability is there. No, that is what I am asking. And
yeah,
so that the other way that we're discussing the discussion in the question answer forum and all such things, it is there. It is going. It is going through proper way. It is going. But from your side, what I am asking, actually, any numericals will be there, and a similar kind of one more examination I am going to face. That means characterization of polymer elastomers and composite. The same thing I am facing in the last moment. It is a Paka theory part, but last moment some questions are coming. And not
yeah.
at all is discussing in the lecture part. Okay, it is another case, and you please this also from your as a TA. It is just I am bringing to your notice also.
Okay, I will take care of it.
Right. Thank you.
Yeah. Okay, thank you for joining.